Good afternoon, everyone. In this lecture, we will start talking about how to calculate the magnetostatic law, the magnetostatic field, right? So how do we calculate the magnetostatic field from different sources? We established that the source for the static magnetic field is going to be a charge flow or a current density flowing in a volume. It is going to be some kind of current. So the question is, and that's how the magnetic field was understood historically, and how people started to try to quantify it. So the question is, how do we tie between the sources of the magnetic field and the magnetic field? How do we calculate it? What is the equivalent of Coulomb's law for the magnetostatic field? So the magnetostatic field gives us a way to calculate the electrostatic field from a point charge. What is the equivalent law that will allow us to calculate the magnetostatic field from a current, whether it's a condensed current in a wire, or a charge distribution that's moving with a certain charge density, right? So there are two main historically developed laws to calculate, and those are both empirically figured out. So people did a lot of experiments, and they came out with those laws experimentally. It was later that those laws were put on a solid theoretical foundation by James Clerk Maxwell. Okay, so the two laws that we're going to study are the Biot-Savart law from the two French scientists, Biot and Savart, and then there's Ampere's law, also a French scientist. So we're going to start with the Biot-Savart law. And this is an empirically discovered law, right? So the setup. So we want to have our coordinate system as usual, right? And then we're interested in calculating the field as usual. We're interested in calculating the field at let me use a different color. We're interested in calculating the field at a point. All right, so this is the position vector R for that point P. What is the source of the field? The source of the field is a wire, a thin wire. By thin meaning you can ignore its width. It's just a small wire, also called a filament, right, that carries a current. So here we're assuming that all the current, so Biot-Savart law is a law of finding the magnetic field from a filament, right? So we assume that all the current is condensed into this wire that has no width, it only has length, right? And then the idea is that we can chop up this wire into small parts, and each small section of the wire is going to be a current, right? Different current element. So this is going to be a current element, right, at this point, for example, right? And now this current element, or this element of the wire, has a length dl prime, right? L is the length of the wire. dl prime is an element on the length of the wire, length element, and we said we use the prime system if we're describing coordinates on the source material, right? So this small element here, let me do it in red. So this small element has current flowing in it, right? And so this small element is a distance r hat from the point where we are. R prime is the distance r prime from the point. No, I shouldn't do it like this. Okay. So this is Yeah, this element is a distance r prime from the origin. So r prime is the position vector for the source element, right? And then the distance from the source element of the magnetic field to the point in space I'm interested in calculating the magnetic field at is going to be r capital, right, vector. And again, as usual, r magnitude is going to be the magnitude of the vector, right? And r vector capital is from inspection is going to be r minus r prime. Okay, so this is the setup for the Biot-Savart law. So we have the current in a filament, we chop it up, we take one small element, and we can say we can calculate the electric field, magnetic field, sorry, due to this element, right, with this setup. And the field coming from the whole wire, from the whole current, is going to be just the summing up of all the elements. So what is the magnetic field dH from one element? So this is going to be I, the current, times dl prime times sine lambda. I think this is the Greek symbol lambda, yeah, right, over 4 pi r squared amps per meter. That's the unit of the magnetostatic field intensity, magnetic field intensity, right? We said we wanted to start with H because H is not dependent on the material, and then we can calculate B as mu H, where mu is the magnetic susceptibility of the material. What is lambda? Lambda is the angle from between the current flow. So lambda is this. So this is the angle of the current flowing in the element versus the vector pointing to the point in space where we are calculating the field. So this is lambda, this angle. Right? And notice if the angle is 90 degrees, this is 1. If the angle is 0, meaning that the current is moving towards the point, there is no magnetic field. It's going to be 0. Okay. So this is the element. What about the whole field? The whole field is going to be H is the magnitude of the field. Let me start with the magnitude. The magnitude of the field, so H is magnitude H. Right? The magnitude of the total of the field at that point is going to be the integral. So I'm going from point A to point B, let's assume, and then there's no current beyond those 2 points, right? Typically that won't happen. Typically you would either have an extended wire that goes to infinity on both sides, or a wire that goes in a loop. But assuming that the wire starts at point A and ends at point B, we get the magnitude of the magnetic field intensity to be the integral of this term, which is I dl prime sine lambda over 4 pi r squared amperes per meter, right? And what about if I wanted to get this is just the magnitude. This is still not the Biot-Savart law. I'm just setting it up, right? We want to now capture the magnitude of the magnetostatic field, of the magnetic field intensity, right? So typically, what happens here is that the right-hand rule applies. So if your thumb points towards the movement of the current, the direction of the current, and your fingers point towards the point where you're interested in finding the field at, the field needs to be 90 degrees with respect to your palm. Okay, and so the field direction will be in this direction, going out of the page. Right? It's hard to draw, so I won't draw it, but imagine it going out of the page. Right? So I want to express this, by the way, vectorially. Notice here we have sine of the angle. Right? So remember when we were studying vector calculus and vector algebra, when did the sign appear? The sign appeared when we were doing the cross product, while the dot product appeared when we were using the dot product. We got a cosine in the expression. When we were using or defining the cross product, we got a sine in the expression. So I should expect to be able to rewrite this in terms of the cross product, right? To encode the sine in the expression for h. Right? So if I do that, I finally get the final form of the Biot-Savart law. So it looks like this: 1 over 4 pi integral from the start point of the current to the end point of the current, I dl prime as a vector. Remember, this is a directed element, cross r, right? R capital. What is R capital? R capital, we said, is r minus r prime, right, over r minus r prime squared, right? But I want to use this just to indicate the direction to the point in space I'm interested in calculating h at. I'm not interested in the dimension or in the magnitude of this, so I need to normalize this. So that's why I put here cubed. One of those magnitudes here goes to normalize this vector, so that I can get h in a direction that's normal to r capital and dl. Okay. So this is finally the Biot-Savart law, and it's an integral law. So what you need to do is if you have some currents, you need to chop them up, and then you need to integrate, mindful as you integrate on you have to be mindful of what is varying as you move along the path of the current along your source, and what is not varying. Whatever is not varying, you can take out. For example, if I does not depend on where you are on the wire, if it's constant, you can take it out. If same with r hat. So typically R is varying, of course, because you're moving along the wire. The distance from the point of the wire or the element on the wire and the point you're interested in calculating the field at is varying, of course. So this will remain within the integral, right? So I could have written this as h equals 1 over 4 pi ab I dl cross r hat, which in this case is a unit vector, right, over r minus r prime squared. Then it becomes a squared. Okay, it's the same thing. Okay, or yeah, I could have just said r squared to simplify. It's the same form. It's the same thing. I'm just saying the same thing differently. But I mean, this is the Biot-Savart law, and it can be used to calculate the magnetic field, static magnetic field due to any steady current configuration. And it's a useful law, especially when you're dealing with wires or filaments, right? So a current element that is infinitesimally thin is called a filament, we said, right? And then we connect those filaments together to construct a wire, right? What is B? B is the same as H. You just add the susceptibility mu over 4 pi, and if it's air, it's going to be mu naught. Let me write it in general. Okay. Now we define the Biot-Savart law for a wire current, right? Current going through a wire made out of, it's a filament, a current filament. Does that mean that we cannot use it to find fields that are due to a charge distribution, J? No, that doesn't mean that. We can still use it to find it for charge distributions, but we have to do a bunch of tricks. For example, we could use it to find the field due to a sheet of current, a two-dimensional sheet that's carrying current, or a three-dimensional, let's say, cylinder that's carrying current. So this would have a current density in terms of amperes per meter squared. This would have a current density in terms of ampere per meter, right? Because right, so I is passing through the total sheet, but each filament of the sheet, right? So that's the idea. The idea is that we take this sheet has current, two-dimensional sheet, has current passing in it. We divide it into filaments. And each filament here has a distance that width that approaches 0. Yeah, so this is going to look like a bunch of wires, filament wires, that are bunched together to form a sheet, right? And each of those filaments, for each of those filaments, we can apply the Biot-Savart law, right? And then individually, and then what do we do after we find the field due to the Biot-Savart law for one filament? As usual, we integrate, we sum over the whole sheet, right? So let's set this up. So this will depend on the problem. I mean, you have to set it up properly and divide your source of magnetic field into filaments, and then integrate over the filaments. So let's take the flat sheet example. I could set it up in this way. I could take my three-dimensional axis, x, y, z, right? And then let's say I have a flat sheet. Let me see, how am I integrating? Yeah, let's take the flat sheet to be where the surface is along the normal to the surface is the z-axis, right? So let's take this to have where the x goes from, right? So it's centered at the origin, and x goes from the x dimension go from L to minus L, so the whole width here is 2L, and then the y dimension go from minus D to D, so it means the length here is 2D. So I'm setting up this way. I want to take my filament to be what? I want to divide my filament along the x-axis. So those are my filaments. So this is filament 1, filament 2, filament 3. This is how I am imagining dividing the sheet, right? So on and so forth. So each filament, so a total current of I is passing through this sheet, coming in from the left and going out from the right, right? Let's imagine that. Then what would be, if the total current is I, what would be the current that's flowing in each separate filament, right? In each separate filament, the total current is going to be I dx, right? Dx is the infinitesimal width of the filament, right? So that will be, I mean, this would be 0 if I have an infinite amount of filaments, because the width of each filament is going to be 0, right? But I'm not getting 0 here because I'm integrating, right? But this would be the current going through, infinitesimal currents going through one filament, right? Okay, and then what would be the infinitesimal magnetic field intensity due to all the filaments? I just need to integrate over all the filaments, right? Minus L1 to L2. I need to integrate along, like as I move. What's my dl, by the way? What's my dl prime in this case? It's dx prime, right? Because sorry, dy prime, because each filament is moving in its direction is in the y-axis, right? It's moving in the y-axis. So if I apply the Biot-Savart law, I get dy prime cross r hat over 4 pi r minus r hat, sorry, r minus r prime square. Okay. Okay. I think I forgot something here. What did I forget? Oh, okay. No, yeah. So this current here gets distributed along the length from minus L to L, right? Along a length of 2L. So what would be the current per strip, per filament? Well, it's going to be dx over 2L actually. Think about that, right? So if dx, if dx presents this dx here presents the portion of the sheet that I'm considering to be the filament. So the total current is I, so the current going through the small filament is going to be equal to dx over 2L, right? If the length is 2L, 2L over 2L is 1, so the whole current, I get the whole current. If I'm want to find the current flowing through half the sheet, that'll be half 2L, which is L over 2L, half of I, right? For a small, the current flowing through a small width, which is the width of the filament, is going to be dx over 2L times I. Okay. So this would be the expression, and I guess the integral, oh, that's a set. Okay, so this is a mistake. The integral needs to be from minus d to d. Okay, right? So this is the field due to a single filament. And this is like a vector field, right? So this is the field due to one single filament here. What about the total field of the sheet? Well, the total field is another integral. So the total field is going to be, I'm going to integrate over all the filaments from minus L to L, right? And I'm moving along the integrating something, right? I'm moving around the x-axis in the x-axis direction, right? I'm integrating this way, and then for each individual filament, I have this inner integral, minus d to d I dx over right, over 2L dy prime cross r hat over 4 pi r minus r prime, okay, squared. So the first integral I'm integrating, I can take, this is dx prime, by the way, right? It's on the material. This dx is on the material, on the source. So dx prime. I can take this dx prime out, right? I took it out, and then I'm integrating with respect. Okay, so I have two integrals. I have an inner integral where I'm integrating with respect to dy prime, and then I have an outer integral where I'm integrating with respect to dx prime. And this is how you do use the Biot-Savart law to do the integration for a sheet. Right? What if I have an example where I want to do use the Biot-Savart law for a 3D object, right? So how would we formulate that? Again, we have to base it on the coordinate system. That's the simplest approach. So x, y, z, and then I have some material that's a thin conductor that's looks like this. Right? So it's not a cylindrical wire, it's like a rectangular wire, square wire, right? And here the length here is h, the length here is k, and yeah, and then I is passing. Okay, so we have a bunch of filaments here. The filament is this, right? So we have a bunch of small filaments that we can divide that into, right? And then we have to use the Biot-Savart law per filament, and then we have to integrate. Okay, and let's see. So we want to use the Biot-Savart to find law to find this the magnetic field due to this sort of object, right? Now this time around, the current, the total current, gets distributed along a cross-sectional area, right? So each of those filaments right, like that. I won't draw the whole thing, but this gets distributed across this cross-sectional area, right? Each small filament has dimensions on that cross-sectional area, has dimensions of well, I mean the thing is is in parallel with the YZ axis, right? So it has dimensions dx, dy prime, dz prime, right? And the amount of current going in each filament is going to be I dy prime dz prime over k times h, the width of the whole thing and the height of the whole thing, right? So this is the amount of current in the filament. Now we can use the Biot-Savart law and say, hey, by the way, the length of the whole thing is L, let's say. Okay, so the field due to a single filament is going to be the integral from 0 to L, that's the length of the filament, I over kh dy prime dz prime, right? And then L is in the direction of x, so we have dx prime cross r hat. R hat is the vector. Let's say I need to find the field here, for example, from this filament. R hat is this vector, the unit vector in that direction, right? Over 4 pi r minus r prime squared. R, of course, is from the origin to the point, and r prime is from the element to the point, right? So this is actually sorry, so this is r, and then r hat, of course, is the unit vector, and then r prime is, this is r, and then this is r prime. R prime is from the origin to the element on the filament. Okay, so this is the field due to a filament. The whole field, the complete field, now is going to be, it's going to be a triple integral, right? So we want to integrate over all the filaments, but the filaments are spread across a cross-sectional area, right? So we have to integrate over two variables, over y prime and z prime, to get the total, to sum up all the filaments. Right? Let me call this point A and this B, and then let's call this point C and this D. Essentially what I'm saying is H equals A minus B, B minus A, just to simplify, and K equals D minus C. I just want to just simplify so I can write this. I can say I'm integrating from C to D and integrating from A to B, right? And then I have a third integral integrating from 0 to L I over KH dx prime cross R over 4 pi R minus R prime squared, right? This is the integration over one filament, and then I have a double integral over to do all the filaments. So I start with I'm integrating across dy prime, and then I integrate across dz prime, and that gives me the total field due to such an object. So when it's a 3D object, I get a triple integral. When it's 2D object, I get a double integral, effectively. When it's a single filament, I get a single integral. Okay, so we will do an example or two during recitation about using the Biot-Savart law, but as we said when we examined calculating the electrical field from charge distributions, typically most problems, unless they have a lot of symmetry, will be very difficult to solve or even formulate the problem. But for some subset of problems where there is some symmetry to the problem, those integrals will become easier, and we could show such examples, right? Because remember, you have to be mindful of everything inside the integral that could change as you're sweeping the integral. So inside this integral, R hat is going to vary depending on where you are. R and R prime are going to vary, and so on and so forth. Okay, so those integrals are in theory easy to write, very hard to solve, almost impossible to solve unless it's a problem that has some symmetry to it. Right. Okay, so that's one way of calculating the electrostatic field. The other way, which is kind of like akin to Gauss's law, in the sense that it's a simpler way for many problems to calculate the magnetostatic field. So remember, in the electrostatic field, we could always calculate using Coulomb's law and doing integrations over the charge distributions. But for many problems, that is very hard to do, and it's easier to use a law like Gauss's law, right? That's easy to apply to very symmetric situations, right? In a similar manner, although we can calculate any magnetic field using the Biot-Savart law, a more fundamental formulation of a more fundamental law that allows us to much more easily calculate the magnetostatic field is Ampere's law. And in many ways, it's the counterpart to Gauss's law, only it has to do with the curl rather than the divergence, right? Due to the nature of the magnetic field. Magnetic fields are fields that are generated by vector sources, by currents, essentially. They're not generated by point charges. Okay, so that will be what we will discuss right now, Ampere's law. So what was Ampere's discovery? Ampere's discovery was where's my whiteboard? Oh, okay, all right. So this is black. Just a second. Okay. All right, Ampere's discovery was the following, and it all starts with the Biot-Savart law. It's just another way to formulate the same thing. That's kind of like where Gauss's law is another way to formulate the same essential result that we got from Coulomb's law. Okay. That is easier to apply in many situations. So if you take this long filament, current filament I, right, and you zoom in, just zoom in on a small part of it. So it's like a straight filament. And then using the Biot-Savart law, we know that, hey, this is the element directed that way. That's the direction of the current flowing. This is the point in space I'm interested in finding the field at. And this is R. So the magnetic field is going to be 90 degrees from both R vector and dl vector, right? But what happens if I rotate a bit? So if I rotate like by some angle, R rotates by this angle, right? Some angle. The field is also gonna stay. L remains the same. R rotates. Now the for H to remain 90 degrees with respect to R and dl, H will rotate a little bit. So H will look like this now. Right? So you notice a pattern arises. If you let me redraw it here. If you have a line like that with current flowing into it, if you rotate around the wire, you notice that the field is rotating as you are rotating around the wire. H, right? H. So, and if I draw it, this is the field picture, the field vector picture. If I draw it using the field line picture, where I draw a line where the point at each line, the tangent at each line represents the direction of the field, right? I get this picture, right? I get a field that's rotating around this line element, right? And whenever you have a circulation, so this is called a circulation. So it seems that naturally the magnetic field around a wire circulates around the wire. Whenever you have circulations, it's natural to ask, what happens if I integrate along this circulation? What happens if I take, so this is the closed curve C, what happens if I integrate H, right? And this is dl here. So what happens if I integrate, I start at a point and I integrate along that circulation? There are, notice there that the field is tangential always to the curve, so there are no normal components to the curve, right? And what turns out is that and this applies from the Biot-Savart law, is that when you calculate this circulation, it turns out to exactly equal the I enclosed, the total current flowing in the surface enclosed by this circulation, right? And this is it. This is Ampere's law. And it makes sense in terms of units too, right? Because if H is ampere per meter and dl is meters, I get ampere, right? So this is Ampere's law, and notice that it's kind of like the analog of Gauss's law, but in Gauss's law you take surface integral, right? You take E dot ds equals q enclosed over epsilon. So this is the counterpart in the domain of magnetics of Gauss's law. And this looks much easier to manipulate and work with than the Biot-Savart law, right? None of those that awkward cross product that you have to do. Right? So this is Ampere's law. It's equivalent to the Biot-Savart law, but in many ways it's easier to apply in many situations, and it is more fundamental. It was easier to mathematically incorporate into the theory of electromagnetics than the Biot-Savart law. Biot-Savart is the kind of law that's a purely empirical law, kind of like Coulomb's law, where people started with Biot-Savart law in the same way people started with Coulomb's law, but ultimately, as they moved on and they started to experiment and think about it more and develop more theory, they started to reach more elegant formalisms, and Ampere's law is the more elegant formalism, in the same way that Gauss's law is the more elegant formalism. Okay. This, by the way, suggests that this is the integral form of Ampere's law. This suggests that there is a point form to to Ampere's law. What is it? What's the point form tied with circulation? So HdL equals I enclosed, right? What is the point form? Well, the point form is this curl H equals J. This is the point form, or the differential form, of Ampere's law. Right? And it follows, we can see how this differential form leads to this integral form, because if I take J, so I take J, if I take J, I'm going to show you that those two are equivalent. If I take J and I integrate over a surface where J is passing, right, I get the total current, right, passing through that surface. So this is going to give me I enclosed. Yeah, J is current density. I integrate J over the surface, I get the total current. And what happens when I integrate over that same surface a curl dot ds? Well, here we can apply Stokes' theorem, right? So this is equal to the circulation over the boundary of this surface of HdL equals I enclosed. Okay, so this differential formalism is equivalent to this integral formalism, and they are both, I mean, the same representation of Ampere's law. Just that the integral formalism of Gauss's law is the same as the differential formalism of Gauss's law. Let me write it quickly again here. So Gauss's law, the integral formalism is, as I said, closed surfaced d dot ds equals q enclosed, and the differential formalism is divergence d equals rho v, the volume charge density. So here we have total charge, volume charge density, and here we have total current, current density. Okay, and we said that I mean, this is all fine, and it's a pretty elegant law that, and its usefulness comes in situations that have a large degree of symmetry, right? You know, in the same manner as in when we applied Gauss's law, we looked for situations where we can do like a Gaussian surface around an object that has a large amount of symmetry, so that we can take the field outside of the integral, and we can find the field value easily. Same way for magnetic examples, magnetostatic examples, we need to find configurations that have a large amount of symmetry. So we need to find configurations where I can take a contour around, let me draw it in another color, take a contour around the configuration, the physical system, such that due to the symmetry of the problem, I know that the field is always going to be tangential to that contour. I want to do that. I want to have this symmetry. Why do I want that? Right? I want the field to always be tangential to this contour. That's one. And two, I want the field to be the same along the contour. It does not vary along the contour. Why do I want to do that? I want to do that so that I can take this outside the integral and solve for it easily. the same way, when I'm doing like a Gaussian surface, I want the d field on the surface to be constant and always be normal to the surface, right? Remember that? If the field is always if it's from the symmetry of the problem, the field is always normal to the surface and is constant everywhere on the Gaussian surface, I can take it outside the integral and the problem becomes trivial to solve. Same thing with Ampere's law. I want to look for contours such that the field, the H field, is always tangential to that contour and constant on the contour. Then I can take it out of the integral easily. We call this in Gauss's law, we call that finding a Gaussian surface. I don't believe it has a name in Ampere's law. I guess we could call it, I could make up a name. I could call it finding an Amperian contour. Let's make up something, okay? But that is the essence of Ampere's law. You rarely, I mean, it's very few problems where we can solve Ampere's law easily when there is no symmetry. It's like you can count them, probably 2-3 problems exist in textbooks, if at that, right? And most problems require symmetry to be able to solve. And many useful systems do exhibit symmetry. For example, so let's do an example. What's the simplest example we can think of? Transmission line. So extended, long transmission line. I want to find the field around the transmission line using Ampere's law. We could have used the Biot-Savart law to solve for this, by the way. So I'm going to do that during recitation, but I want to show you how trivial it is just to apply Ampere's law, right? So from symmetry, if you think about it, at any point in space, right, the current is flowing in this direction, and this is the point, the vector that's pointing to that point in space. So using the Biot-Savart law, I know that the field is going to be circulating, right? Yeah, I mean, just from the right-hand rule and the Biot-Savart law. So my thumb points towards DL, right, and my fingers point towards R, and my palm points to the direction of the field. So I get a field that's circulating around the line. So from the symmetry of the problem, I know that the field, let me erase this, I know that the field is going to be tangential to this contour. Which contour? This contour. So if I draw this contour, see, that's a circle with radius A, right? Let me call it H, right? Right. So this is a circle around the transmission line with a radius H. I know that the field is going to be always tangential from the symmetry and always equal. So it's going to be equal on this contour. The question is, what is the magnitude of this field? Right. So to find the magnitude of the field, we apply Ampere's law. So H dot dl equals total I enclosed. H, we said, is constant, so I can take it out. I'm taking its magnitude, right? And then I'm integrating over C of dl. I'm integrating dl. What is the integration of the line element across a circle? It's just the circumference of the circle, right? So what's the circumference of the circle? It's going to be 2 pi h equals I, right? And so that tells me that h equals I over 2 pi h. And that's it. I found the magnitude of the field with respect to h. The farther am I from the transmission line, the less field will I have. If h is 0, the field becomes infinite, right? But this is it. And just as in the case for Gauss's law, although now we removed the vectorial aspect of the solution, from the symmetry of the problem, we can easily bring it back, right? So I know that the direction of the field is always going to be tangential to this contour, right? So if I bring in some cylindrical coordinates where where this is the z-axis, and h is in the direction of r, and then and so that tells me that the field is always going to be in the direction of phi, right? So that's what the angle is. Right, so this is z, and this is let's say y, and then this is x, and then I know that, right? So x and y are in the plane of this contour, right? So I know that the field is always going to be in the direction of phi hat in that coordinate system. So I can just say I 2 pi h phi hat. I can always put back in the vectorial aspect of the solution from the symmetry of the problem, from the contour, Amperian contour that I choose. I like this phrase, Amperian contour, similar to Gaussian surface. I don't know why people don't use it. It's a symmetrical surface that you assume, contour that you assume, so that you can find the field using Ampere's law. Okay, and that was easy. If we were using the Biot-Savart law, it would have taken us probably 10 minutes to solve for this. We solved it in under 10 minutes, under 1 minute actually. Okay, let's examine the problem further. Let's now assume that there's a certain thickness to the transmission line. So this is an infinite transmission line that has an inner diameter A. Okay, and it has a certain current density J, right? So it has a certain current I passing through it, right? I. So what does it mean? What is J? J is the total current divided by the cross-sectional area, divided by pi A squared, ampere per meter squared. Okay, so now the question is, what is the field, H field, from the center to some distance h from the center? So this is the center of the transmission line, and then this is some distance h. What is the field? Okay, so it's the same. I mean, for the field outside, if h larger than a, Ampere's law applies, we get the same result exactly. It's I over what? Over 2 pi h, right? We solved this, right? It doesn't say, because Ampere's law utilizes the total enclosed current. If my contour is this, the total enclosed current is I don't care about J. But what happens if my contour now is here, is within, I should draw this as an oval to signify that it's a three-dimensional circle viewed from the side, right? If the Amperian contour is inside the conductor now the enclosed current is going to vary, going to be different. So if H is less than, H is larger than A, sorry. If H is less than A, what would be, so let me do Ampere's law again. H dot dl equals I enclosed. Okay, so take h outside of the integral, 2 pi h, same thing, right? The circumference of the contour. Now I enclosed is going to differ. I enclosed is going to be J, the current density that we calculated here, times the reduced surface enclosed by the contour when the contour goes inside the conductor, right? So what is so I enclosed will not be the total I, it will be some less amount of current. So what will that be? That will be J times pi h squared, right? J times the surface area enclosed by the contour, right? And then we know what J is. J is I over pi a squared. Let me put that in. J is I over pi a squared. Okay, so let me do some manipulation now. So J is I over pi a squared pi h squared, right? And pi goes away with pi. I end up with h being, oh, and one h cancels one h here. So h ends up being IH over 2 pi a squared. Okay, so H, depending the electromagnetostatic field magnitude depends on. It's rather unfortunate that we used small h to designate the distance from the wire, but that's fine. It works. So if h is, which is the distance from the transmission line to the point where we are interested in finding the field, let's think of h as a height, right? The height. It would have been better if I used r, but that's fine. If h is larger than larger than a, larger than the radius of the wire, then h is going to be I over 2 pi h, right? And then if h is less than the radius of the wire, if small h, then the magnetic field is going to be IH over 2 pi a squared for h smaller than a, right? So that's an interesting result. If I plot this, if I plot with respect to height, the magnetic field magnitude, so until I reach the radius of the wire, right, h less than a, when h is 0, small h is 0, I get 0, right? And this is a linear function, right? This linearly increases. So it's I is constant, a is constant. So this linearly increases until h reaches a. The value it hits when h is equal to a is I over 2 pi a, right? And then once we hit a, I need to have less than or equal, right? Once we hit a, we get this expression, I over 2 pi I over 2 pi h. So now it becomes the curve, the h curve as a function of h small becomes proportional to 1 over h. So it becomes like a reciprocal function. It goes down like this. Okay. So notice this big difference now. When we assumed this an infinitesimal filament, the field had an expression such that the H field, magnetic field, goes to infinity as we get closer to the wire. But if we assume some thickness to the wire with a current distribution, the field doesn't go to infinity. The field goes to its maximum value when it hits the surface of the transmission line, and then starts going down until it reaches 0 at the center of the conductor. This is a more realistic scenario than an infinitesimally small conductor. Right? As an infinitesimally filament of a conductor which has a radius 0 and it's just a very thin one-dimensional thing is a mathematical construction. That's why we get infinite fields around it. The same way where a point charge has infinite fields as you get closer and closer and closer to that point charge. Those are mathematical constructs. They are useful in many ways, but they are not realistic. They are useful because they are not realistic, because they make many problems easier to solve. Okay. So yeah. So I guess we can go through more examples of applying Ampere's law, right? And in the next lecture. Right, and hopefully we can close out the magnetostatic chapter next. Right, and yeah, this is just exactly the same motions you go through as when applying Gauss's law, and it's just very easy to apply and very useful. All right, so we'll discuss this further later. Thank you.